Good morning, everybody. Today we not only have a Codeforces round, but we have Codeforces Educational Round 104. I'm about a minute and a half late, so we'll jump into it right now. As usual, solutions will be at the end of the video to all the problems I know how to solve, and I'm going to do my thinking kind of on this whiteboard here. So you can see how okay, old title, anyway. So you can see how I think through different problems, if you're interested in that. For the problems that I need to think for. All right, problem A. You have n heroes that are fighting against each other in an arena. Initially, the ith hero has level AI. Each minute, a fight between two different heroes occurs. These heroes can be chosen arbitrarily. It's even possible that the same two heroes were fighting during the last minute. When two heroes of equal levels fight, nobody wins. When two heroes of different levels fight, the one of the higher level wins, and its level increases by 1. The winner of the tournament is the first hero that wins in at least this many fights. A possible winner is a hero such that it exists a sequence of fights that hero becomes the winner. So it's the number of things that aren't the minimum. Very cool. So, the multi-test case, yes. And what we want to do is enter a n or a equals fs.readArray fs.nextInt int n equals a.length, and then let's sort it. So if I is not equal to a at 0, then ans plus is out the answer. For those of you who are wondering what ruffle sort is, in Codeforces, a lot of the time in Java, in Java at least, arrays.sort uses dual pivot quicksort, which is usually, which is usually a very fast way of sorting. However, if you pick the wrong pivot every time, it actually turns out that it's n squared. So we don't want an n squared sort, and in order to fix that, we shuffle the array randomly beforehand. That way, the pivot we pick is random, so it's expected to be n log n instead of n squared. Suppose you're living with two cats, A and B. There are n napping spots where both cats usually sleep. Your cats like to sleep and also like these spots, so they change their napping spot each hour cyclically. Cat A changes its napping spot going backwards, and then continues again. Cat B goes forwards. Cat B is much younger, so they have a strict hierarchy. A and B don't lie together. In other words, if both like to go to spot X, then A takes this place and B moves to the next place in its order. Okay, so yeah. I see. N is at least 2, and presumably after the first collision there aren't any more collisions. Is that the case? Let's try it. 1, 2, 3, 4. So we have A, then we go back to the beginning, then we have B, go back to the beginning. So if it's even, there's no collisions. Let's try it with n equals 3. We have A. Then we have B. So B skips to this. Then the next step, B would want to be here, but it can't be, so it skips to this. Then the next step, B would want to be here, but it can't be, so it skips to this. Okay, so that's kind of weird. Interesting. What about 5? What does it look like for 5? So then it does conflict with this, so it's there. Okay, so we're interested in the number of things before the first conflict and then the number of things after. And that's, we also want to know how many conflicts there are. Alright, so let's see here. You have n and k, so n equals this, k equals this. So if n mod 2 is 0, then there's no conflicts. So we can just print the answer, which would be n minus 1 minus k under mod plus 1. Okay, so when is the first conflict? N over 2. So it's after that many steps. Well, n over 2 plus 1. Yeah. So if k is less than or equal to n over 2, then this is the answer. Then go to the next test case. We should probably just make a method for this. So private static int go back int k then indent. All right, so otherwise, int conflicts is 1. So now the question is, how many moves does it take for us to get a second conflict? So we have to move n minus 1 spaces. So it's n minus 1 over 2 turns. Right, so it's 5, so 5 minus 1 is 4 over 2. Every 2 turns we get a conflict. Okay. So conflicts plus equals n minus 1 over 2. And then we want to print go back k plus conflicts. An n space board. I think that's it. Okay, what's wrong with this? This is void. And then we should be good. Okay, so Let's see if this works. 1, 2, okay, this should be 1. Two, 1, 3, 2, 2. Darn, that's very annoying. Really? Yeah, so I get all of the easy, wait, no I don't. I get this one wrong. I get this one wrong too. 3, 1? Nope. 3, 2. I say 2, which means presumably there are 0 conflicts. Wait a minute. So if it's equal to 1 on the one turn, okay, so that should be less than. I think this is just not necessary at all. Really, why would that happen? Yeah, so just simplify this to that, please. Oh, because we start just like we would right after a conflict. Okay, yep. Oh, wait. One, 2, 1, 3, 2. This is wrong. 5, 5. So 0, 1, 2, 3, 4, 5. I print 3. Is it not 3? What is it? It's 2. First hour, A is on spot 2. Oh, I have these orders backwards. Darn. Okay, so this is just. So this is that. And this conflict. Yeah, so this is K-1. Then this should just be. This is out K mod N. That's how many per conflict, and then int actual conflicts equals K over per conflict. Good. That took way longer than it should have, but we got it. All right. Big football championship will occur soon, and teams compete in it, and each pair of teams will play exactly one game against each other. There are two possible outcomes of a game. The team might tie, both teams get 1 point, one team might win a game, winning team gets 3, losing gets 0. The score of a team is the number of points it gained during all games that it played. You're interested in a hypothetical situation when all teams get the same score at the end of the championship. A simple example of that is a situation where all games roll in ties, but you want to minimize the number of ties as well. Interesting. I am going to go to the bathroom. I'll be right back. All right, so one thing I want to check, if you have an odd number of teams and it looks like this, so if you have an odd number of teams, you play that, and then it would be 1 minus 1, 1. Wait, so this would be even actually. So it would be, yeah, so even. Well, yeah, okay, so if you have an odd number of teams, it's easy. So the question is, what if it's even? Does it have to be all ties? For 2v2 it does. What about 1, 2, 3, 4? So you can have a win, a win, a win, and a win. Then these are ties. Yeah, so if we decrease the degree of every node by 1, then after that we can find an Euler tour. Because now every node has 1 win and 1 tie. Yep. Okay. Is there an easier way of doing this so we don't have to code up finding an Euler tour? That is the next question. Maybe. So we can say like win, loss, tie. Loss, win, tie. Well, what if we did this? So 1 and 2 tie, and then 3 and 4 tie. And we do win, loss, win, loss. 1 beats 3, loses to 4. 2 beats 3, loses to 4. Uh-oh. So that means 3's lost twice. Okay, what if we pair up 1 and 2? So they tie here, and then win, loss, loss, win for everyone else. Yeah, there you go. That works. Tie up here, win, loss, loss, win. Okay, that's a constructive way of doing it. Good. So D. Oh, this is C. All right. If n mod 2 is 0 is the hard case, otherwise this is easy. Okay, otherwise we have an int array grid, new int array n by n. We need a space after this. Then for this grid, we need to print it. So it's like the same thing as this, really. All right, so then how do we fill this in? Yeah, so for int I equals 0, I less than I plus plus. I plus equals 2, maybe. So then grid I plus 1 equals grid I should be 0 if it's a tie. Okay, so I minus 1 equals 0. For in j equals 0, j less than n, j plus plus. J is equal to I, or j is equal to I minus 1. Continue. We should probably start at I plus 2 even. Good. So then grid at I j equals 1. Grid at I j plus 1 equals minus 1. Grid at I plus 1 j equals minus 1, grid at I plus 1, j plus 1 equals 1. So what does this look like? 0, 0, 1, minus 1. I think that's fine. Okay, and then yeah, it should be fine. Wrong answer test 2, huh? I see. More likely this part, probably. Nope. It's this right here. Order of operations. We might right answer again, though. Okay, pass test 2. Do we need print writer? Oh boy. Burning submits like crazy. No, probably not. We should be fine. Or, well, we're printing 10 to the 6 things. Ah, darn. Okay. All right, move on to problem D. Pythagorean triples. Pythagorean triple is a triple of integers a, b, c such that it's possible to form a right angle with the lengths of the first something, the second something, and the hypotenuse equal to c. Yep, 3, 4, 5. Vassia studies properties of right triangles, uses a formula to determine if some triple of integers is Pythagorean. Unfortunately, he's forgotten the exact formula, but he remembers only the formula was an equation with squares. So he came up with the following formula: c equals a squared minus b. Obviously, it's not quite right, but to Vassia's surprise, it actually worked in the triple 3, 4, 5. According to Vassia's formula, it's a Pythagorean triple. When Vassia found the right formula, he understood that his formula was wrong. He wondered, how many triples are there such that they are Pythagorean according to both definitions? So we want to see if a squared plus b squared equals c squared, and if a squared minus b equals c. N is up to 10 to the 9? Alright, well, this is easy enough that we might as well just write a brute force to see when it happens. So it looks like it only happens when These two are 1 away. So if this thing squared equals the difference of two adjacent squares. So we can brute force this smallest number, we can brute force A. See if it's equal to the difference of two adjacent squares. So, well, what is n squared minus n minus 1 squared? It's equal to n squared minus n squared plus 2n. Minus 1 equals 2n minus 1. Okay. Wait, this happens for every odd number. Yeah, well, that makes a lot of sense. Yep. So, okay, so if, yep, okay, well, good. I don't have a proof for why it only happens here, but it probably does. So if this is what, if n, okay, so if a squared equals 2n minus 1, then we have a squared, something we don't care about. Well, this is just c minus 1, yeah. And the last one is a squared plus 1 divided by 2 squared. Okay. So I guess we need to pre-comp all of the answers. So we'll put all of the square numbers in this tree set. I is less than squares dot add long I times I. All right, good. Wait, that's not what we want. Yeah, okay. This is unhelpful. 4 into I equals 3, I is less than 10 to the 5th, plus. Plus equals 2, because only odd numbers work. Okay, so 1c equals I guess a squared, okay. Then we just want to print this. Query get value. We're set. Excuse me. All right, so let's try this. See if we're getting the right stuff. I c minus 1 c. Twenty-four, 25. Wait, we're not subtracting two numbers, are we? We want the difference between these two to be a squared. These aren't square numbers. Yeah, a squared equals b plus c. Oh, so these are just, yeah, and then the difference between these two is 1. So it's just super easy, barely an inconvenience. C equals just that, right? 3, 4, 5, 5. Yeah, okay, good. Why would that be the case? Long. Submit D. I do floor, yeah, okay. Should be super fast. Got it. Yeah, we're not doing great. That's fine. Not a problem. E, cheap dinner. Ivan wants to have a good dinner. A good dinner should consist of a first course, second course, drink, and dessert. There are N1 types of first courses. The ith one costs AI, N2 types of second courses, ith cost BI, N3 types of drinks, and 4 types of desserts. Some dishes don't go well. There are M1 pairs of first and second courses, M2 pairs of second and drinks, M3 pairs of drinks and desserts. Ivan wants to buy exactly one first course, second, drink, and dessert. The total cost of the dinner should be minimum possible. Well, yeah, so the pairs are first and second, second and drinks, then drinks and desserts. This is a cool problem. I like it. So if, yeah. So suppose you know you have first, second, okay, well you've got like more than that really. So you've got your A choice, B choice, C choice, and D choice. So if I told you what your B is, like if you know what this is, then it's just the first A that doesn't conflict. So each B has an easy, it's just like the max. So we can do that for each B. Same thing for each C. We have each of these. Then for a B, you just choose the first C that doesn't conflict, right? Oh, I guess you want these might not be increasing. So sort the B's and C's by their value. Yeah, okay, that's pretty easy. We can do it. So yeah. single test case, I guess. Yeah, single test case. Makes things a bit easier. Int array ends equals fs dot read array of size 4. Int array a's equals fs dot read array now equals is 2d. Okay, so we have all of this read in. After we do that, we need to read all the pairs. Oh wait, this is the cost. Okay, these are the costs, okay. We also probably want a sorted version. Now we need to sort this. Can't use lambdas, that's really annoying. Okay. Is there a better way of sorting this? Guess we can make this an integer array. Oh, sorted index at I. All right, so this will give us the sorted version of each index. Yeah. So we have both of these, and then we also want illegal C's for B. Illegal C's for B, same thing. Times it 2, illegal D's for C, new hash set, okay. Int and edges. So illegal A's for B at from, or at 2 dot at from. And this will be illegal C's for B at from dot add 2, and then illegal D's for C at from dot add 2. Okay, so for B equals 0, B is less than ends at 1, B plus plus. Yeah. So if we can't match this, otherwise break, ten to the 8, so we'll give it like 5 times 10 to the 8. Yeah, okay. So then A is at 1, B plus equals 2 add. Otherwise, 2 add equals A at A end, and then break. Oh, A is at 0, and yeah. Okay, so now we want to do the same thing with the C's. So C equals 0, all the way up to N2, C++. 2 add equals this. This is going to be the D index and sorted index at 3. If illegal D's for C at C contains D index continue, otherwise this equals 3 at D index. A is it to C plus equals 2 add. Okay. I want to do this thing again, resort them, and then we want to match each B. make an infinity here so we don't have to worry about it. All right, so matches B with a C, sorted index of 2, legal C's for B, at B contains C index. All right, so then what do we want to do here? Check all the B's. Okay, this should be, is it 1? Yeah, okay. Good, I think that's it. We're gonna just do this. Okay. 26 minus 1. Submit. Lots of code, but that's fine. All right, looking good. How are my friends doing? They're doing all right. Pretty cool. Awesome. Test case 50. Got it. What was our time limit? 4 seconds. We're fine. Awesome. Given a positive integer n, you have to well, hang on. How many solves does this have? This has 2 solves. Okay, this has 5 solves. So maybe read both. Given a positive integer n, you have to represent n as the sum of integers consisting only of digit 1s. Oh, you can use pluses and minuses. Gotcha. Interesting. It's an ugly problem. You have C1 letters A, C2 letters B, C26 letters Z. You want to build a beautiful string of length n from them. Obviously, you cannot use the ith letter more than C times. Each Ci is greater than n over 3. A string is called beautiful if there are no palindromic continuous substrings of odd length greater than 1 in it. Abacaba is not beautiful, but it has several palindromic. Oh, because it. Okay, that's a run-on sentence, but that's fine. Another example is the string ABCAA, which is beautiful. Calculate the number of different strings you can build. Oh my goodness. Well, The array doesn't matter. Right? Surely it doesn't matter. If you have more than n over 3 of a certain thing, then yeah, that's not. Like, okay, so the array obviously doesn't matter because, like, you've got some spaces here, right? If you have, let's do 6, so it's nice. So what we want to do is place 3, we want to place 3 x's here. So if we place like an x here, and an x here, we have to place another x, let's place it here. Then we've placed an x that are 2 apart, right? There's a gap of 2 here, which means no matter what we place here, this will be a palindrome. So you're like, the number of these letters you have doesn't matter at all because you have enough of the letters that it's not going to be constrained at all. So the question is just how many strings are there with no odd palindromes? We need no odd palindromes in the first half, no odd palindromes in the second half. But also, like, is it easier to count how many strings of length n have at least one palindrome? Maybe. Because then we know what that palindrome is, at least. Although there is some include, like, it's annoying because there's some overcounting that will happen. Hmm. Yeah, this is hard to do. If we say there's an odd palindrome, then we need to like make sure there's no odd palindrome before it. So we still have to like avoid placing palindromes at all. Otherwise we'll overcount. So it's 26 for 1. The answer for 2 is 26 squared. Six, 7, 6. Then 16900. And then 422500. Not on OEIS. That's good. What if we tried inclusion exclusion? So well, the problem is these palindromes can be overlapping in weird ways. Yeah, honestly, I'm not sure. I'm not sure. Nice job, TFG from Brazil. Well done. It's very impressive. And Rainbow too. Number of strings of length n with no palindromic substring. Really? Okay. Observe that a string does not contain any palindromic substring if the string does not have any palindromic string of length 2 and 3, because the palindromic substring of greater lengths duh. Yeah, of course. If you have a palindromic substring of length 3, then you have a palindromic substring of length 5. If you know, of course. Any first grader should know that. Yeah, okay. All right. Okay, this is an easy problem. So, well, I guess we can read this if we want. If n is greater than or equal to 3, then it's m times m minus 1 times m minus 2, choose n minus 2. Why is that the case? There are m ways to choose the first symbol, m minus 1 to choose the second. Oh, but it can be equal, so it's not quite that. So we have m ways to choose the second, and then we have m minus 1 ways to choose the third. So, yeah, okay. Let's try it. So, there are 26 ways for the first, 26 for the second, because the second letter can be anything, and then 25 for the third, because it just can't match the first character, 25 for the next one, etc. Okay, so long ants equals, well, what's the mod? Long mod equals this thing. Why is this bigger than 26 cubed? Wait a minute, what? Oh, it's not. Okay, what am I doing that's so silly? N equals 2. Yep. 0 IQ play right there. Good. No, really? Okay. Is that really the case? Oh. Wait. Why is that a problem? I shouldn't be overflowing lungs. Yeah, it shouldn't break anything. Why would it not be? So are they saying there are, well, there aren't that many palindromic substrings of length 3. Why not? Okay, do we need like a DP for this or something? What's going on? You place a letter here. Let's say you place an A. Then you place another A here. Now you can place anything here until you place a B. So here you have -1. Here you can place a B. Okay. Here you can place anything that isn't a B. You can't match that, so you place an A. Can you replace anything? It isn't a B, so you place an A. What's wrong with this? Why is it not? First two, you have 26 choices for. Everything else, you have 25. String is called beautiful if there are no palindromic contiguous substrings of odd length greater than 1 in it. Abacaba is not beautiful. It has several palindromic substrings of odd length greater than 1. For example, ACA. Another example, the string ABCAA is beautiful. Sure is. Calculate the number of different strings you can build and print the answer modulo 998244353. Am I going insane? Oh, wait. Yeah, okay. So you can run out. The array does, yeah, okay. You can run out of one character. Can you run out of 2 characters? Yeah, you can run out of 2 characters too. So we need to see, okay, how many can you not build? So we want to say how many ways can you run out of A? How many ways can you run out of B's, etc. But you could run out of both A's and B's. So in this case, you have 1, 2, 3, 4, 5, 6, 7, 8. You have 8 characters, so you could have 3 A's and 3 B's. You can't make this string because you run out of both A's and B's. So you'd run out of A's, run out of B's, but then add in run out of both. Cool. Yeah. So we need a DP of, I guess, characters 1, char 1s, char 2, what the last one was, and also our index. So this is going to be n by n by 3. What our index is n. So n cubed times 3. 10 seconds, we can do that. Okay. Wait, okay, so we need to run out of both A's and B's, not one of them. Yeah. Okay, so we need 2 DPs. This will be int A's. last int index. Let's do this in a way that makes more sense. And then we need a go-to that has last index and then these as well. Static mod equals this. It's a memory limit, a gig, awesome. Static long array dp. All right, so come on, DP2. Good. We're set. So now we need to actually write these DPs. Okay, so if DP at last index is not equal to -1, return DP at last index is. Otherwise, return this. I guess we can make these longs. That's fine. Okay, so if last is equal to 0, then wait, hang on a minute. We need the last one and the one 2 steps ago. Okay. So if last equals 0, then okay. If index is equal to, let's not call this index. Let's call this letters left. So if letters left is equal to 0, it's equal to 0, yep, continue. Then return is equals 0 one way, otherwise there's 0 ways. a is equals math.max if a is in 0. Okay, well, a is less than 0 is probably what we want. Okay, so now a is equals math.max if a is in -1. And we need plus 1s everywhere that we look at this. Plus 1, good. Okay. So if last is equal to 0, then we can't place an A. There are 25 things we can place. Things we can place times go 1 of second last. We just placed a thing that's not an A. How many letters do we have left? Letters left -1, and we have the same number of A's left. Otherwise, place an A. Well, we can always do this. So, oh wait, no we can't. So in this case we have 24 ways of doing it. Because there's one letter we can't place, and it's also not an A, so it's this. Otherwise, ways plus equals go 1 of second last. We placed a 0, which is an A. Letters left -1, A is -1. Okay, so that's this first DP. B's needs to do the same thing. Okay, so this is letters left. DP2, A is +1, B is +1. DP2 at this. DP2 at this. Okay. A's is less than 0, and B's is less than 0. Okay, so if there are 0 ways initially, yeah, so this part we basically have to redo. Okay, so if it's not equal to a 0, then we can place an A. Okay, anyway, we'll worry about that in a minute. Then ways plus equals go to second last. Then we placed a 0. We have letters left -1, A's, B's. A is -1. If last is not equal to 1. Oh, this is really easy. We don't actually need this first DP. We could just say we have 0 of the second thing. Anyway, if the last, wait, no. Yeah, we do need the first DP. Because we want to place all 26 letters, not 25. Okay. Figure that out in a minute. If ways is not equal to 1, then we can place a 1. Place a B. So ways plus equals this. We placed a 1. Letters left minus 1. Same number of A's, but 1 fewer B. Okay, so equals 20. Well, okay, so last equals 2. If it does, then there are 24 ways. Otherwise, there are 23 because we can't place an A or a B or whatever this third thing is. Okay. Ways plus equals go to second last, place 2, letters left minus 1 fewer letter left. Where am I? How many A's? Same number of A's, same number of B's. This is general ways times this. Okay. All right. So, good. Read array, size n. How big can these things get? Less than n. Good. All right. 4, 5 equals 0. Nope, not size n, size 26. Less than 26, plus plus. Ants. Voice crack. Anyway, ants minus equals go 1 of, what was the last thing? Whoa, there is no last thing. Okay, this is if last is equal to 2. All right, so we can do this now. Ants minus equals go 1. Last thing was a 2. Second last was a 2. Letters left are n. How many A's are there? A, I. Okay. Alright, so the last was a 3, second last was a 3, letters left. How many letters left do we have? N. How many A's do we have? A at I. How many B's? B at I. A at I. Or AJ, I mean. Thank you. This out. Okay, ants equals ants mod plus mod again. Uh-oh. Uh-oh. Taking a long time. Oh no. Whoa, no. Oh no, 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 no. Please don't be this slow. Okay, so we have trouble. We need to call this iteratively, it looks like. Why is this so slow? 401 times 401 times 401. Nope. It is a problem. Is the last one the index? This one should be instant. DP should be instant. So if we skip this part here, oh, there we go. That's a problem. That's a bug. So this one should be, this should be very quick now. Yeah, good. Okay, so it's just this part that's slow. Okay. Huh. Alright, so we need to call this iteratively then. So this is, where does this look? It looks at, the letters left always decreases. Okay, so what is letters left here? At the moment it is the third thing, last third thing. So let's make this 2. All right. That should speed it up massively, memory-wise. Then we just need to make it iterative. Letters left is less than or equal to 2. Or, yeah, up to n. Yep, okay. So letters left increases, and then everything else doesn't matter. Last, second last, is and b's. Last, second last, letters left, A's, B's. Okay, let's move this to the front then. Oh, nope. Well, that's DP1. I guess we'll move it to the front in both. Okay, then this goes to the front. Nope, not there. Okay. Good. I think we're fine there. So in this case, arrays, we just need to do this. Fill this with -1s. Good. Now this needs to be letters left and 1 everywhere. Wonder if this works. And we crashed. 401. Yeah, okay, less than 400. Oh, okay, yeah, these need to be 402 then. Less than or equal to 400. Exception 2. DP2. What? Letters left, less than or equal to n. Oh. And 1. Okay, does this work? Moment of truth. Hello? Why is it so slow? Wait, what? Yes, it's just this DP2 is super slow. Darn. How much time? Oh, only a minute left? Oh, no. Ah, it's not right. Okay. Huh. This is kind of annoying. Well, I'm almost there. It's probably a bug in my DP somewhere. Yeah, I guess I don't have enough time to debug it. darn. Okay, almost. Not a great performance, but that's fine. Yeah, very close to G. Cool. Awesome. Well, yeah, that's the contest. I guess let's go over solutions now. To everything but F. I know how to, I don't know how to do F. I didn't really spend much time thinking about it. It's probably digit DP. But, yeah, here we go. Okay, so problem A, arena. So you have a bunch of heroes, and you have a bunch of pairs, and there are a whole bunch of fights. And then a winner is the person who, wait. Oh yeah, the first person who has basically infinity wins. After there's a particular fight, whoever has the higher level is the winner, and their level gets incremented. So the question is, if you choose the fights in whatever way possible that you want, who can be a winner? So the idea here is you can always just beat up on the weakest guy. So if there's someone who's worse than you, you can just keep fighting them infinitely. And then as long as you're not the smallest person, you could win given sufficient number of matches. So the question is basically, how many elements of the array are not the smallest element? In order to do that, it's pretty easy to implement. All you have to do is sort your array, and then count how many elements in the array are not equal to the first element, and then print that answer. So yeah, that's problem A. Pretty easy, pretty straightforward. Problem B, you have two cats. They have some napping spots, and the first one will go backwards in time. The second one will go forwards in time. The first one goes from n minus 1 all the way down to 1, and then it keeps going back from n minus 1 all the way back. But the second cat will go in order from 1, 2, 3 all the way up to n. However, if he's ever in the same place as cat A, he'll move one space ahead cyclically. So the question is, after some amount of time, where is cat B located? So what we can do to solve this is draw out the cases a little bit. The first case that we're interested in is if it's even. Where do I have even? I don't have even. So let's say the number of spaces is even, maybe it's 4. So we've got space 1, 2, 3, and 4. It's a little big. Initially, cat A will be, let's make sure these colors match. A is red, okay. Initially, cat A will be at space 4, and then it'll move to 3, and then it'll move to 2, and then it'll move to 1. Cat B will start at position 1, and then it'll be at 2, and then it'll be at 3, and then it'll be at 4. In particular, after 0 steps, or I guess at time 1, so at any odd time, B will be in an odd position, and at any even time, A will be in an odd position. So they're never going to hit each other. There will be no conflicts, and in this case, B just takes one step forward each turn. So B's position is just equal to the time modulo n. So it goes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, or it might be easier to think about it as 0, 1, 2, 3, right? So it starts at position 0. So if after 0 seconds, it's at position 0, 1 second, it's at position 1, etc. So that's the first case for B. Let's look at that. So I have K as the number of moves it has, and then I do everything 0 indexed. So if K mod 2 is 0, the answer is just K mod n. But now, okay, so that's the first case. The other case is, what if it isn't even? What if the number of spaces is odd? And in that case, they run into each other. So let's draw that out a bit. Got 5 spaces here. In this case, you have A goes like this. And B will go like this. So you'd have a conflict here. So then B moves over. And then you have another conflict right here. So B would be here. So here's your conflict. Here's your conflict. Then B's here. Then B's here. And then you would have a conflict here. so B moves here. So in this case, what happens is you could imagine, hypothetically, having a conflict right here. Might make things easier. So you can imagine, instead of B starting at position 0, you can imagine B actually starts at position 5. But then right off the bat, you move B over to position 0 because there's a conflict. So in this case, every 2 steps, there is a conflict. If n's equal to 3, every 1 step, there's a conflict. Every step, they would wind up being in the same position. In general, what happens is they're at this conflict, right? So in this case, the number of spaces between them, you've got the 2 here, the 1 here, the 5 here, and then the 4. So in total, they are going to meet up in the middle. So they each need to move n minus 1 over 2 steps in order to reach this next conflict space. And then, again, there's a conflict here, so they each need to move over to here. So they each need to move 2 steps, which is n minus 1 over 2 steps to reach the next conflict space. So you know every n minus 1 over 2 turns, there will be a conflict, and you know how many turns there are, which means you know how many conflicts there will be. Every time there's a conflict, B moves forward 1 step. So it's the total number of conflicts plus the total amount of time will be how many steps B moves forward. That under mod is where B ends up being. Hopefully that made sense. So, okay, that's just not real code. So there are, every n minus 1 over 2 turns, there's a conflict. And then the total number of conflicts is the number of turns that you take divided by that number. So there's your solution to B. And then initially my code was a bit messy because I thought B moved backwards and A moved forwards, but yeah, I just misread the problem. So yeah, cool. That's the solution to problem B. Awesome. Let's move on. Keep moving. Problem C, minimum ties. So you've got this big football championship and you want to have the final score of every team be the same, but you want to do that so that you have the minimum number of total ties in the game. You get 1 point if there's a tie, or 3 points if there's a win, 0 points if you lose. So yeah, this was a bit messy here, but anyway, I can explain the idea. What I did is I just did kind of an ad hoc constructive solution. So if, let's say the number of teams is odd, what that means is if this is your team, right, let's say this is you, that means from your perspective, there are an even number of other teams out there. So what you could do, hypothetically, you could win half your games and lose half your games. In that case, what that means is that you're going to have the same number of wins and losses, so this will be kind of sustainable, and every team could do that. And that's like what we're aiming for. But if the number of teams is even, you can't win half your games and lose half your games. You're either going to have to win more than half or lose more than half if you don't have any ties. So that's not possible, because if you win more than half, then not everyone can keep up with you. Not everyone can win over half their games. Someone's going to have to win half or less, because like there aren't enough wins to go around, right? Pigeonhole principle or whatever. So yeah. So this is like some optimal solution. This is what we're aiming for. In order to get this, what we can do is give every node a label. So we'll say we're 1, yours is 2, this is 3, this is 4, this is 5. And we'll say when 1 faces an even number, it's a win. When it faces an odd number, it's a loss. And then for 2, we'll kind of make it go backwards, right? Oh, can we please go away? Thank you. For 2, when it faces the 1, then it needs to be a loss. When it faces the 3, it should be a loss. Or I guess we'll say, yeah, how do you distribute these? Well, let's just draw a 2D table here. So if we just have like some columns here, so we've got 1, 2, 3, 4 versus 1, 2, 3, 4, 5. Sorry, 5 teams. In this case, we want win, win, and then that would make these ones here losses. So 2 versus 1 is a loss, 4 versus 1 is a loss. And then we'll put losses here. We're obviously going to have like zeros down the diagonal because no team plays itself. And then we can continue with this pattern. So win, loss, and then we can say win. I guess we'll color this in the opposite color. So this will be win, loss, win. These will be losses. Okay, the colors are not helpful here. But yeah, so you get the idea. This is going to be a loss and this is a win. So each team will have the same number of wins and losses with this construction. Yeah, they each have half of the wins, half the losses. Because in the row, you have an X here. Other than that, it alternates wins and loss every turn, other than your X. So that's a solution if the number of teams is odd. If the number of teams is even, what you can do is you can, well, I'll just do an example here. You can get rid of, or you can like, yeah, so we're going to need at least one tie per team because it needs to be sustainable, right? You can't have more wins than losses because not every team can do that. So we'll like pair up teams on like sets of 2. So when 1 and 2 play each other, this will be a tie. But then for the rest of the teams, we can alternate wins and losses. So this will be a win and loss, this will be a loss and a win. And then we have to mark the opposite here if we want to complete the table. So when 1 plays 3, it should be a loss, loss, win, win. So now here, what we can notice is we'll take steps 2 at a time, right? So we did 2 here, we could do another 2 here. So if it were 5, 6, then we would have a win and a loss, and this would be a loss and a win. So we fill out this whole row at a time, which means for each person, it has the same number. It gets 1 win and 1 loss for both teams, right? When we fill in this 4 square, the 1 gets a win and a loss, and the 2 also gets a win and a loss. They both have 1 tie initially. So in total, every team is going to have 1 tie because they'll have 1 partner, and then they'll have the same number of wins and losses because every time you give them a win, you also give them a loss when you fill in this 4 grid all at once. Okay, hopefully that made sense. Yeah, here's the idea. Here's what the code looks like. So if there are an even number of teams, it's kind of tricky. This is where I did the partner thing. So yeah, you versus your partner both tie, and then I do this 4 by 4 or the 2 by 2 grid, the 4 spaces at a time. That's one way of doing it. I'm sure there are other ways of doing it too, other constructive ways. And then I just print the answer at the end. Otherwise, I just print this grid alternating plus and minus 1, depending on whether I plus j is even or odd. And that's it. That's problem C. Okay, problem D. We have D, E, and then G left. Okay, problem D. Pythagorean triples. I don't have a proof for this, but what you can notice is that there's some math, and if you see, nope, problem D. If you just like, so you want to see when these two things overlap, right? When is the formula they give you actually a Pythagorean triple? And if you run it, you'll notice here are the cases that work. So 3, 4, 5, 12, or 5, 12, 13, 7, 24, 25, etc. What you'll notice here is these numbers are always 1 apart, right? So B and C are always going to differ by 1. And yeah, you can probably prove that with math. I think probably 60 or 70% of people at least didn't prove it with math, or if they did, they first found out that it was true and then proved it, but they didn't like go through the math and come up with a proof. I don't know, maybe you did. If you did, let me know in the comments. That'd be interesting. But that seems kind of unlikely because this is like just so easy to write a brute forcer for. So yeah, so you know these two have to differ by 1. Really what that means is they're like 2 interesting numbers that you have to look at. There's the A and then the C. The other thing here is that the c is going to be on the order of a squared, right? It's about a squared big. So your runtime can be order of square root, and then you can find the answer to all of the queries. In this case, I won't even go through, well, actually, maybe I can go through the math. Let's see, where did I write it? So, yeah. So, okay, you have a squared plus b squared equals c squared, and a squared minus b equals c. You can move the b over to the other side, so then you have a squared equals b plus c. You want to find out when that is the case, where b and c differ by 1, right? So we saw from the pattern that b equals c minus 1. So really, what we know is a squared equals c minus 1 plus c, which is equal to 2c minus 1. So when does a squared equal 2c minus 1? Obviously, this means c is about on the order of a squared, right? So a, we only need to check up to like 10 to the 5th in order to get c up to 10 to the 9. So we're going to check all of the a's, brute force the a's, and that will give us the answer for all the c's. The interesting thing here is this is like a very easy thing to get. So anytime we have an odd number, if you square an odd number, it's going to be odd. So we'll have a solution here. So for every odd a, we'll have a solution for c. Yeah. So cool. There you go. So what that means is that if this is a, then I guess we can make a formula for c, right? So if a squared equals c, or wait, what was it? A squared equals 2c minus 1. That means a squared plus 1 equals 2c, or c equals a squared plus 1 over 2, where a is odd, of course. So, yep, that's our formula for c. A squared plus 1 divided by 2. Don't forget to use longs. And then I just put that in the hash map. So I stored for this value, how many things are there. Then for each of the queries, I just say, well, if it's less than 5, the answer is 0. Otherwise, I want to look at the last time there was some valid triplet. So I take that triplet, and then I print the answer there. And that's it. That's the problem. Here we go, that easy. This would probably be a map in C++ if you're doing that. Okay. The last problem is problem E. What was E? Cheap dinner. This was a really cool problem, actually. I really like this. Yeah, so day after Valentine's Day. It's kind of funny. They have that that problem. Anyway, so cheap dinner. Yeah. You have a bunch of dishes of 4 different types. So you have like type A, type B, type C, and type D. For each of these, you have a bunch of prices. So maybe you have like, I'm going to do them in sorted order, but they're not given to you in sorted order, but I'm going to sort them here. So 2, 3, maybe you have 5, and then 6 for type A. For type B, maybe you have a 3, a 1, and a 5. Oh, I said I'd do sorted, so 3, 4, and then 10. For type C, maybe you have a 1 and a 2. For type D, you've got a 5, a 6, and then a 100. So you also have, in addition to having these different dishes of each price, you have some pairs that don't work well together. So maybe you can't get the 2 and the 4, or the 10 and the 6, or the 1 and the 5, the 1 and the 2. Or you might have some B and C pairs, right? So maybe you can't have a 3 and 1, and you also can't have a 10 and 2. Yeah, maybe these are the pairs you can't have. So in particular, you only have certain types of pairs. You have A's and B's. There's some A's and B's you can't have. There's some C's and B's you can't have, and there's some C's and D's you can't have. There are no pairs of A and D that don't work together. There are also no pairs of B and D, or of C and A. So it's a pretty simple set of illegal things. There are only like adjacent things in this line here. Okay, so what can we notice? Well, A and B are pretty simple. Each A has no constraints on it other than the B. So what we can look at here is, like, let's say we have this 3, right? We're going to match this 3 with whatever thing in A we want to that's cheapest. So this 3, we can like imagine joining this 3 with whatever thing in A is cheapest. In this case, this 2 is what we would match it with. So the 3 and the 2 we would match. We would say if we take the 3, we're also going to take the 2 here. What about the 4? Well, the 4 can't match with the 2 because 4 and 2 don't taste good together. So the 4 we would match with the 3. And then this 10, we would match the 10 with the 2 because there's no edge saying we can't, so we do that. If we store for each item in B a set of all of the things that can't match with, we can find all of these items. You might say, oh, it might be n squared, right? Because each pair, that might be illegal. We might, for each thing in B, we might look through all the things in A, so it might be n squared. But that's not true because they can't give you that many things since input is limited. So for each thing in B, we'll look until we find something. In worst case, we're only going to find the number of things they told us are illegal in input as bad pairs. So we're not going to find that many things. So this is actually like order size of edges. This is like order m. We can find all of these things. And then we're going to do the same thing for the pairs with C. So this 1 can't match with 5 or 6, so we'll match it with 100. And then the 2 it can match with 5, so we'll match the 2 and the 5. So when we're done with that, we just have 2 groups. We have the A's and B's combined and the C's and D's combined. And let's like resort them. So we resort them by value. Yeah. So after we do that, we have this 2 and the 3. These are now worth 5. The 4 and the 7, or the 4 and the 3 are worth 7. And the 10 and the 2 are worth 12. And then on the B side, we have the 1 and 100 are 101. And the 2 and the 5 are worth 7. We need to add our edges back in. So the 101 can't match with the 5. The 7 can't match with the 12 either. So these are the edges we can't have. Now again, we have a similar version of this problem, but it just looks like this. So here are the B's and here are the C's. We want to match this B with the first C that isn't illegal. In this case, it's the 5 and the 7 should match. We'd want to match the 7 with the first C that it doesn't have an edge to. So again, it would match with the 7 here. Then we'll match the 12 with the first C that it isn't illegal. So we can't match 12 and 7 because there's an edge, but we can match the 12 and 101. Then we take the best of each of these. In this case, that would be the 5 and the 7, and our answer is $12. That corresponds to picking the 5, so we would pick this here, and the 7, which is this here. So we would take the $2 A, $3 B, $2 C, and $5 D. Cool. Hopefully that makes sense. I'll show you the code. Code's a bit messy, not gonna lie. Yeah, oh well. So one of the things I did here in order to make it a bit cleaner and not have to make a bunch of objects is I have these sorted indices. So it's like if you go through all of the dishes in order of their cost, where are they cheapest and where are they most expensive? So first of all, I read in how many of each item there are, and then I read in the cost of each item. And then I go through and make, for each type, I make the sorted order of those types sorted by price. Okay. Then I make sets for which A's are legal for a given B, which C's are legal for a given B, and which D's are legal for a given C. I just read those in from input here. So these lines are all just like reading in that input. Lots of stuff. All right. After that, I have this sweep. So first, I match the B's with A's. I match each B with the first A it hasn't seen. I'll walk through this logic here, but then this happens a bunch again. There's a lot of copy paste going on. But for each B, I go through each A in sorted order, and if I can't match with it, I keep going. But otherwise, I say I'm going to match this B with this A because I went through it in sorted order. So the first one I see is going to be the best one. So I match it, and then I keep going. Okay, and then I add it to its price. I do the same thing for C's and D's, and then I resort the B's and C's column. Actually, I resort all of them, but this is good enough. Yeah, I resort the B's and C's, and then I try and match the C's with the B's. Finally, the answer is the best B that I haven't seen. So and a's at 1 is like the cost of the b's. So I go through all of the b costs. And now really it's going to be the b cost plus the b matching with the a. And then each of those I match with the best c and d. So that's what this is here. So this is like really a group of the best 4 defined by the b. And then at the end, if I haven't found any pairs, that means I never would have changed this from infinity. So my answer would be infinity, or something bigger than infinity. So I print out -1 if that's the case. Otherwise, I print out whatever the answer is. Awesome, very cool. I don't know how to do problem F. I suspect it's some sort of digit DP where you keep track of like what the carry bit is, but that's annoying, and I didn't really feel like working on that. So I didn't do F, I did G instead. And I have the idea for problem G, but my DP is slightly wrong. There's like a bug somewhere, and it's really hard to debug because the only input they give you is huge. So I can't debug it live, but I can give you the idea if you're interested in that. So initially, I thought that this array doesn't actually matter because an element can't appear more than 1/3 of the time. But that's not the case because you are allowed to have even palindromes. So let me give you an example of what that might look like. If you have the following string, like this is allowed. You're allowed to have A, B, B, A, B, B. In this case, what is the problem first? So you have a certain number of copies of each letter. You can't use more than that of each letter. But you want to count how many strings can you build where there are no odd palindromes with length greater than 1 in that string. So it can't have like ACA, it can't have abacaba, can't have ZZZ, but it can have AA as long as it doesn't have any odd palindromes. Now, this string here has n over 2 A's. Also has n over 2 A's, n over 2 B's, and it's legal, importantly. Which means we can run out of characters, which I should have noticed, obviously, because Codeforces in general is not in the business of making hard problems with these stupid, like, random constraints. I don't know. So yeah, so I should have noticed that. But it didn't show up in the first 2 samples, it did in the third. So there you go. Now, you have to watch out for that. But like one important thing you can realize is that you're not going to run out of a lot of characters. You might run out of 1 character. In fact, you might run out of 2 characters, but you're not going to run out of 3 different characters. So that makes it pretty simple. There you go. You're going to run out of 1 character or run out of 2. The next thing to notice is if we're looking at odd palindromes, if you have some odd palindrome of length 5, maybe you have A, B, C, B, A. The way a palindrome works is these 2 characters have to match and these 2 characters have to match. But if it's an odd palindrome of length 5, right in the middle, you have an odd palindrome of length 3. So I got kind of confused and had to look this up in the middle of contest, which is allowed because Codeforces. But it's kind of a very obvious thing I should have known. If you have some odd palindrome and you don't want any odd palindromes, as long as you don't have any odd palindromes of length 3, then you're fine. So there you go. So you just have to get rid of all palindromes of length 3. All right. So how do we do this counting? We're going to do a DP. So some DP. What we're going to store is let's talk about the counting first, then we'll do the DP in a minute. Let's not get too ahead of ourselves. Basically, the total number of strings that we have is let's say how many strings are there where there are no odd palindromes of length 3. So for the first choice, we have 26 characters. Let's not worry about the counts yet. We have 26 characters for the first choice, 26 characters for the second choice. But then for the third one, it can't match this first choice, so we have 25. Then the fourth one can't match this, so we have another 25. This one can't match this. So whatever this character was, we can be anything other than that. So there are 25 choices here. There are 25 for the rest of these. So we can calculate whatever this number is under mod very easily. There you go. So there's that. Now the problem is we might run out of characters. So we have to subtract something from this. We want to subtract what happens when we run out of each character. So in order to count how many ways there are to run out of A's, but make a string that has no odd palindromes, in particular no palindromes of length 3, we can do a DP. So the DP looks like this. We'll have some DP. We want to store what the last, or what like the character 2 back was, what the last character was. Then we want to store what index we're at, and we also want to store how many A's we have. So there's the DP. But this number of A's is not, it doesn't really matter that it's an A. It could be any character. So we can reuse this DP for all 26 letters by just storing this as like a general number, right? So this is just the number of characters you have left. It doesn't need to be the number of A's. Then you have some choices here. In particular, you have 2 choices. You can place an A, or you can place anything else. So you have 25 ways of doing this. In particular, you have to be careful because this is only 25 in the case that the last character you placed was an A. If the last thing you placed was an A, or it's the beginning of the string. If the last character you placed wasn't an A, then you only have 24 ways of doing this because you can't match whatever this one was. In particular, you don't actually have to store what this is in your state. You just have to store whether it's an A and whether it's the beginning of the string. So there are only 3 possibilities here. It's an A, it's like nothing, hasn't been placed yet because it's the start of the string, or it's something else. It's a B, C, D, E, doesn't matter what it is. Yeah, so that's the idea. So there's your transition, order 1. DP runs in order 1 times the state size. So this is 3, this is 3, this is n, and this is n. So n squared times 9. I think. Am I missing something? Yeah, that's right. Okay. So then that's the first DP. The issue is this doesn't actually work because you can run out of both A's and B's, for instance. So if that happens, you're over subtracting, right? You subtracted out how many ways there are to run out of A's. You also subtracted out how many ways there are to run out of B's, but you might be able to run out of both A's and B's for the same string. So you have to add back in the strings where you ran out of both of those because you just subtracted it twice. So, okay, so how do you store that? Let's say you're going to run out of both. So you want to add that back in. In order to do that, we can do a similar DP, but we need to store the character that was 2 back, the last character, our index, the number of A's, and also the number of B's. And this will be size n as well. That also makes these both size 4. And then the DP gets a little more complicated. You can place an A, you can place a B, or you can place something else, but it's still pretty similar. So yeah, my code has a bug, so I guess read it with care. But this is what the second DP looks like minus the bug. That's what the first DP looks like minus the bug. And then here's the counting. So we subtract out every way of including one number once or more, and then we add back in the number of ways that it's illegal to have 2 different characters. Yeah, hopefully that made sense. Voice crack, again. Anyway, cool. So that was the contest. I thought this was a really good problem, despite not solving it. It was kind of annoying to debug, but that's just how it is. Honestly, I liked a lot of the problems. So cheap dinner, I thought was really good. Pythagorean triples, I didn't really prove the math for, but it's probably pretty good. I like it. A was really good. I thought B was a little annoying, but I guess that's fine. And what was C? C, I don't know. C was constructive. So, yeah. I wasn't a huge fan of C. But I don't know. I thought it was a good set. Overall, I really liked the contest. I thought it was good. Pretty good balance. Maybe not in the perfect difficulty order, but still, if you readjusted the problem difficulty, the problem order, I think it's pretty much perfect. Awesome. Well, I hope you enjoyed the contest. Hope your rating went up if it was rated for you, and have a great day. That's all from me. Goodbye.